Hello friends, I'm now going to take you on what I wish to do through this lecture series. We have what is known as advanced calculus, and then I'm going to give you a general visualized picture of what advanced calculus is all about. But let's not forget that it's a big ocean by itself. So this calculus follows what is known as the elementary calculus. But what is advanced calculus? Let's begin from there, right? So let's look at what topics are generally discussed in advanced calculus. One is differential calculus. Now, when we talk about differential calculus, there are two aspects: the differential calculus of single variable functions and the differential calculus of multivariable functions. Obviously, multivariable functions require higher knowledge, and of course, you must be well grounded in single variable calculus to even think about multivariable calculus. So what are the situations where we encounter differential calculus? You can see on the screen two graphics that I'm showing. The left one shows how one can mathematically calculate what is known as the curvature. So when a curve meanders, assuming that it's continuous and smooth throughout, as it moves, we find that it's bending at different rates at different points. So therefore, we need a measure to calculate the so-called curvature, and the symbol kappa is what represents the curvature, and you can see there are four scenarios there. So that is one of the very nice practical applications of single variable differential calculus. On the right, you can see a three-dimensional surface which has got certain local peaks, local valleys, and a very big peak and a very big valley. So in the context of function optimization, we require multivariable differential calculus. So these are the two simple examples that I would like to explain to motivate you towards differential calculus. The second area is, of course, integral calculus. Just as in the case of differential calculus, there are two aspects. We'll have the integral calculus of single variable functions, and then we have the integral calculus of multivariable functions, which we generally call multiple integrals. So again, where do we see these things? So you can see that on the left side of your screen, we have got a surface that is generated through a revolution process. So surfaces, as you can imagine, are generated by revolving arcs about some axis. It need not be always the x-axis, it can be y-axis, or it can also be some oblique axis. So to precisely estimate how much is the surface area when an arc revolves, we can use the integral calculus of single variable functions. And on the right hand side, you can see that we are trying to estimate the volume of a solid. And this can be explained only through so-called multiple integrals. And we'll be looking into these aspects. So there are two things that I just discussed: the differential calculus of single and several variables, and then the integral calculus of single and several variables. The third area, which is indispensable in a scientist or engineer's study, are differential equations. Differential equations govern dynamical systems, and there are again two classes: one, the ordinary differential equations, and two, the partial differential equations. Obviously, partial differential equations require higher knowledge, but we cannot rule out the importance of differential equations involving a single independent variable. So where do we encounter differential equations? When it comes to ordinary differential equations or the so-called differential equations involving a single independent variable, one of the best examples we can talk about is projectile motion. So you can see in the graphic on the left-hand side, a footballer is kicking the football towards probably the goal post, and you can see the trajectory is a parabola. So of course this is set to the gravitational field of the earth, so therefore it's always parabolic. And on the right hand side, you can see fluid flow through a medium, and therefore this is governed by partial differential equations. So it's extremely difficult to um, solve some partial differential equations. So I'm just giving you the context. So on the ordinary differential equation side, we have projectile motion, and when we come to partial differential equations, we have fluid flow. Then a very important part of advanced calculus is the so-called vector calculus, where we talk about the differential calculus of vectors and the integral calculus of vectors. So it's a very rich field, and this is required for studies in electromagnetic fields and in fluid flows. So where do we come across vector calculus? On the left hand side of your screen, you can see a fluid. Uh, Within a fluid flow, we have got a rectangular solid like structure, and we are trying to measure in this particular case how much is the flux across all the 6 faces. So that is a very important study in vector integration. And on the right hand side, you can see how we are trying to find out how much is the work done by the field in moving a, let us say, a particle across a cross section of a pipe. Of course, here you should observe several things. The cross section is probably circular. But what is very important is not the shape, but whether it's closed or open. It's a closed curve, and it is bounded by an open surface. So this is a very important situation. I will talk about these things. Two major theorems are involved in these two graphics, about which at the moment let us not venture. But these are the basic areas, wherever fluid flows or magnetic fields of force are involved, then vector calculus is required. Then we have tensors, the very rich field, and tensors are really very useful tools, particularly when we talk about nonlinear mathematical models that we see during tsunamis and earthquakes and other applications like that. So you can see on the left hand side, the graphic is one where earthquake activity is being modeled. So we need the tensors there. The ordinary vector calculus many times will not work out. And on the right hand side, you can see it's a tsunami somewhere in the southern part of the US or somewhere. And therefore, tsunami and earthquake modeling requires very special mathematical tools, and tensors provide that for us. The sixth important area is improper integrals and special functions. Of course, here I'm not showing you any graphics for the moment, but they're extremely important in handling some very complicated mathematical areas. So we'll talk about, but I just keep in mind the topics that I'm touching. So we need special functions to handle improper integrals which arise in real world situations. Then we've got Fourier series and Fourier transform, which is a very rich area of applied maths in an advanced calculus. And Fourier series can be seen within the human body. because even if you take the heartbeat, it's highly periodic in a healthy person. So therefore, wherever there is periodicity, Fourier series will automatically step in. And then when you try to uh, sort of work in the complex domain or the Fourier domain, we need a transform for that. So a Fourier series, when extended in a special way, becomes a Fourier transform. And where do we see this part of maths? So on the left hand side, you can see the ECG of a patient. So that's a periodic function, and therefore we need a Fourier series for that. And then you can see on the right hand side, it's an example of an image compression problem where the original JPEG image is about 824 kilobytes, and then using some lossy compression technique, using Fourier transform, let us say, is reduced to just 74 KB with not much information lost. And if we can further reduce by another 50%, you will find that still the features are preserved. Maybe some information is lost, about 80% loss in information, but visually not bad. So in image compression applications, we see the Fourier transform. Complex analysis constitutes another major field of advanced calculus, where a complex problem or a difficult problem in the spatial domain is transformed to the complex domain for easy comprehension. And we generally see this in neuroscience applications. So this graphic shows how the brain matter is actually transformed to a much easier interpretable mass. And this happens using complex analysis and the concepts of conformal mapping. And of course, there is a field called manifolds, which are also coming into play here. So complex analysis is a very great field that itself deserves special segment. Then we got differential geometry and manifolds, a very important thing. So in fact, differential geometry is extremely important when we talk about space research and all that, because the ordinary analytical or Euclidean geometry does not cater to many of the situations there. So differential geometry and manifolds are seen there. Then there is something called exterior calculus, about which I will talk about later. But this is a sort of a fairly decent collection of topics of advanced calculus. And of course, in the initial part of my lecture series, I will be touching upon the calculus of multivariable functions, which includes the differential calculus of multivariable functions and integral calculus of multivariable functions. So it may not be in the same order that you are seeing, but all these topics fall under my area of interest, and I am planning to deliver fundamental lectures in all these things, and then we can talk about specific applications in real world problems. Thank you very much.